Have you ever wondered how spacecraft actually move through space, how we reposition them, or what it takes to escape a planet's gravity? Well, then you're in the right place. I'm Eric Hillsberg, and today we're taking a dive into the fascinating world of orbital mechanics. If you find this video valuable, please like and subscribe, and as always, if there's a topic you'd like me to cover, let me know below. Let's start with some cosmic ground rules. Johann Kepler gave us 3 laws that form the basis of our understanding of how objects move in space. Real orbits aren't perfect circles, but ellipses. Oval paths with the central body at one focal point. This means satellites vary in distance from their central body throughout their orbit. Sometimes closer, sometimes further away. A line connecting the planet to its satellite sweeps out equal areas in equal time periods. The practical effect is that satellites move faster when they're closer to the planet and slower when further away. This is angular momentum conservation in action, a fundamental principle governing orbital motion. The square of a satellite's orbital period is proportional to the cube of its average distance from the central body. Simply put, satellites further away from their planet take longer to complete an orbit. If you're looking for a more in-depth explanation of these laws, check out my previous video where I go over the math and cover a MATLAB example. From these laws, we can build up a couple important intuitions before we get into orbit transfers. As mentioned in Law 2, a satellite's speed isn't constant. It changes dramatically based on its distance from the planet. When a satellite is closer to the planet, it experiences stronger gravitational pull, which accelerates it to higher speeds. Conversely, in higher orbits, gravitational attraction is weaker, resulting in slower orbital velocities. This isn't just a minor difference. We're talking about speed variations that can be hundreds or even thousands of meters per second. And here's a counterintuitive fact. If you apply thrust at just one point in an orbit, you'll actually return back to that exact same point in subsequent orbits, but the entire rest of the path will change. With a single engine burn, you'll reach either the highest point, apoapsis, or the lowest point, periapsis, exactly 180 degrees from where you fired your engines, and then you're going to return back to your original burn location. This is why precise burns are very important. A tiny touch can send you on an entirely different path. Alright, now let's get into the meat of it. What happens when we want to move a spacecraft between 2 different orbits? Enter the Hohmann transfer. It's the most fuel-efficient method. It's like changing lanes on a cosmic highway. First, you create an elliptical orbit that precisely touches both your start and target orbits. You use 2 carefully calculated velocity changes, and this minimizes fuel by taking advantage of some of the orbital mechanics principles we just talked about. The Hohmann transfer assumes 2 instantaneous velocity changes, which is a reasonable assumption given that the engine burns typically last just minutes, while orbital periods are measured in hours or days. This elegant maneuver works for both raising and lowering orbits. We use it when deploying communication satellites to geostationary orbit, repositioning weather satellites to cover different regions, and even adjusting the orbits of space telescopes, all while conserving precious fuel. Hohmann transfers aren't limited to Earth. The same principles apply to interplanetary trajectories, essentially performing transfers between planetary orbits around the Sun. But before heading to other planets, we must first escape Earth's gravitational influence altogether. Right, let's talk about escape velocities. This is the minimum speed needed to completely break free from a planet's gravitational pull. The math behind escape velocities involves balancing kinetic and potential energy. As you move further away from the planet, the energy required to escape decreases. At Earth's surface, you need to hit about 11.2 kilometers per second. That's fast enough to go from New York to London in less than 10 minutes. Contrary to what movies might show, spacecraft don't simply launch straight up to escape Earth. In reality, reaching escape velocity isn't an instant process. The extreme acceleration and atmospheric heating at 11.2 kilometers per second would destroy most vehicles. Instead, rockets follow curved trajectories that account for Earth's rotation, atmospheric drag, and energy efficiency. Most missions first reach a parking orbit, like low Earth orbit, where the escape velocity requirement drops slightly to about 11 kilometers per second. From there, the spacecraft needs much less additional velocity to escape since it's already traveling at orbital speeds, which are about 7.8 kilometers per second in low Earth orbit. This multi-step approach is mirrored in rocket design through staging, where spent fuel tanks and engines are jettisoned during flight, shedding dead weight and dramatically improving efficiency. This means less fuel is needed to increase your velocity. As I just mentioned, there's another practical consideration when launching: rotational boost. Launch sites near the equator get a significant speed boost from Earth's rotation. Our planet spins west to east at about 1,670 kilometers per hour at the equator. By launching eastward, spacecraft can essentially borrow this rotational velocity, reducing the amount of fuel needed to reach orbit. This is why locations like Cape Canaveral in Florida and the Guyana Space Center in French Guiana are prime launch sites. Their proximity to the equator provides a natural velocity advantage. Let's take a quick look at the math of achieving an escape velocity. We can calculate this speed from an equation for the total specific orbital energy, which must be conserved. It is defined as the sum of the specific kinetic energy, velocity squared over 2, and the specific potential energy, negative g, the gravitational constant, times m, the mass of the central body, over r, the distance from the central body. To escape, the kinetic energy must be at least equal to the negative potential energy. This gives us an equation for the escape velocity. Another easy way to calculate the escape velocity in any orbit is to find the velocity of a circular orbit at that height and multiply by the square root of 2. One insight from this inequality is that escape velocity depends on how far from the central body you are. To better understand this, let's take a look at an elliptical orbit around Earth. At periapsis, it is greatest, and at apoapsis, it is least. But since the object will be traveling its fastest at periapsis, and we must take the square root of r, it will require the lowest delta v, or change in velocity. This is known as the Oberth effect. All Keplerian orbits follow geometric patterns called conic sections. Picture slicing through a cone at different angles. You'll get circles, ellipses, parabolas, or hyperbolas. These aren't just mathematical curiosities. They're the exact shapes spacecraft follow. Circular and elliptical orbits keep objects bound to their central body, while parabolic orbits represent the exact escape velocity case. Hyperbolic trajectories occur when an object exceeds the escape velocity. And something a little counterintuitive happens. Once the object has excess kinetic energy, the excess velocity is faster than the difference between the current velocity and the escape velocity. For instance, 0.4 kilometers per second of extra speed results in over 3 kilometers per second of excess velocity. This is all well and good, but these are all simplifications, and space isn't as simple as just one planet pulling on a spacecraft. In reality, everything pulls on everything else. To make this manageable, we use a clever simplification called patched conics. Imagine bubbles around each planet where that planet's gravity dominates. Inside Earth's bubble, we only calculate Earth's pull. Crossing into Mars's bubble, now Mars's gravity rules. This method divides complex trajectories into manageable segments, making interplanetary navigation possible without solving nearly impossible equations. By combining Hohmann transfers with patched conics, we've created an interplanetary highway system. First, we plan a Hohmann transfer from Earth to, say, Mars's orbit around the Sun. Then, we use patched conics to calculate when to leave Earth's sphere of influence, coast through interplanetary space around the Sun, and enter Mars's sphere. We can then make up for these simplifications through small delta V adjustments. Space travel isn't always straightforward, and there are some limitations to be aware of. Timing is everything in space missions, where you have to launch well before the target planet is in position. Launch windows are specific periods when the alignment of planets and orbits make a mission most feasible. If you miss your window, you might have to wait months or even years for the next optimal opportunity. Real-world rockets also don't perform like their perfect theoretical models. Factors like fuel efficiency, thrust capabilities, mechanical constraints mean that theoretical orbital calculations remain just that, theoretical. We must calculate inefficient, long trajectories, or use some of these advanced techniques like gravity assists and the Oberth effect. Gravity assists use the gravitational pull of planets to gain extra speed and change trajectory without expending additional fuel. It's like a cosmic slingshot that can dramatically alter a spacecraft's velocity and path. And we talked about the Oberth effect earlier. If you burn engines at the lowest point of an orbit, periapsis, you get maximum energy efficiency. The faster you're moving, the more effective each unit of fuel becomes. And this can be used with a gravity assist for an even bigger boost. One last thing to note is that we've been talking about spacecraft with chemical engines. Spacecraft with continuous, low-power engines require entirely different trajectory planning compared to those of the traditional chemical rocket. Ion engines might be slow, but they can provide consistent, efficient propulsion over long durations. This means we need to use different methods because the instantaneous change in velocity assumption no longer holds. Space is incredible, and orbital mechanics is the magic that lets us explore it. Every launch, every spacecraft, every mission relies on these fundamental principles. What do you want to hear about next? Drop a comment below, and don't forget to like and subscribe. See you next time.